So last time we introduced the multiplication rule. And that tells us that if we have a bunch of events in a sample space, the probability that all the events happen, all the n events happen, it can be written as a multiplication of conditional probabilities. The probability of first event times the probability of second event given that first happened, times the probability of third event given that the first two happened, etc., all the way to the probability of the last event happening given that all the prior events happened. And the reason that this is so, you can see algebraically that will be true, because you can see probability of E1 multiplied by probability of E1, E2 over E1. So I can construct this telescoping product, and in this product, the numerator on the left cancels the denominator on the right. So when you carry out the cancellations, the only thing that survives is the last numerator because it has no denominator on the right to cancel it. Good. And each of those fractions you recognize as conditional probability, which I hope you understood when we introduced that concept. Okay, so that's very important. There are there's really up to now very little theory. It's just this: do you understand why conditional probability is defined the way it is defined? Yes, so that it's not just arbitrary formula. Good. And we covered a bunch of problems. We spoke about the matching problem again. It sounds like somebody is strangled, is being strangled there. Do you hear that sound? Okay, good. I don't want to know about it. I'm not going to be called by the police to be a witness. Yes, thank you. So then we introduce the Bayesian formula, Bayes formula, and that introduces conditioning. Remember that? So I can figure out the probability of E in terms of probability of F and not F. And the reason for that, you can see by the formulas, E is equal to E intersect F or not F. In other words, if E happened, in addition to that, I know that either F or not F has happened. And those are disjoint events because you cannot have both F and not F happening, right? And so the probability of E is the probability of the sum of E intersect F and E intersect F complement. And this is just an intersection. I can use the conditioning. I assume F is the first event, right? So it would be probability of E given F multiplied by probability of F. I'm using multiplication rule here, right? Where instead of reading the multiplication rule from left to right, I read it from right to left, as in Hebrew. Good. Everybody understands how I get this formula, guys? I hope you talk to me, right? I did have an explosive, irritated comment there in the morning yesterday, but then I haven't slept too well for my calculus students. So you understand, guys, everything that I'm talking about. Probability of E intersect F complement is then this expression. Good? And we solved one problem like this. We actually solved a few problems. We remember we finished with the multiple choice type of question here, right? If you want to go over anything there, again, mention so that I will repeat it. And the next question was inspired by this. Okay, so let me show you this very quickly.
Тебе еще никто не при... Ну, так скажи. Папа. Филя. Как при чем? Скажи, папа, ты при всем.
Иди там, вот дядька крупный, один, второй. Не бойся, не бойся, не бойся.
Он тебя выдержит.
Я тебе мечтал.
You get the point. You can watch all 11 minutes later. If we run out of time, as I did write the next lecture, we can watch this. So in Russia, my friends, as in all savage countries, you can, for a small fee, pet an exotic animal, a lion. I would definitely pet a lion. Why not, right? You live once, so to speak, right? So this is a question for you. An autistic savant wishes to pet a lion in a Russian zoo, where petting lions is allowed for a small fee. He cannot tell a bad lion from a good lion, but knows that bad lions bite with probability 0.9 and good lions bite with probability 0.4. If the savant gets mauled by a lion, what is the probability that he went to pet the bad lion? And here you can see those two lines. So go ahead, calculate the probability.
Can you scroll up a little bit so I can see the other number?
Yes, it's very simple. It's 0.9 for this guy and 0.4 for this guy. So you understand this question, yes, guys? If the lion bit, what's the probability we're dealing with the bad lion? Thank you, Chapeli. Okay, thank you, guys. Thank you, Abhishek. I'll just wait a little longer for the rest to finish and then we go through it. Okay, Melissa and Naomi are saying the same thing. I mean, interpret and Naomi. Okay, Alejandro, thank you. Thank you, Sofia. How are you doing, Melissa? Wonderful. All right. Are you ready, guys? Let's go through it. So it should not be too hard. Here is what we are trying to observe. So we labeled this as the bad line and the second as the not bad line, right? So we are interested in the probability that the bad line was the one biting, given that somebody was biting. Yes? So then it's much easier to solve it the other way around. It's much easier to solve biting given bad line, right? When we have information about it. So we are just writing it as the unconditioned probability. And then we write this multiplication. We now can choose which is first, which is second. So we're going to say this is first event and then this is second event, right? So that's probability mild given that it's the bad line, probability that it was the bad line. Yes, divided by the probability that someone is going to bite. And that we can condition based on bad line, probability of bad line, or not bad line, probability of not bad line. Yes? And now this is the extra condition. I mean, we are supposing that's why I mentioned savant. Savants are not able to interpret facial expressions. Like I cannot interpret your facial expressions. So that means that the likelihood that the savant approaches the bad line or the good line is the same. We just cannot tell the difference between them. So we assume it's 1/2. So that means we can cross away the probability of B and probability of B complement. And we're just dealing with this probability, right? Mold given bad line divided by mold given bad line plus mold given not bad line, which is 0.9 divided by 0.9 plus 0.4, which if I multiply, so you said correctly, right? This is 0.9 over 1.3. Some people say like this, but you can just multiply by 10, both and bottom. So it will be 9 divided by 9 plus 4 or 13. Just multiply by 10, it's nicer. And that's approximately 69%. Good. So wonderful that you all figured it out. I'm very happy. So you're learning it very fast. So then the next question is actually perhaps rather appropriate given that the situation still continues. The following is perhaps very relevant in the medical test-loving society of righteous hypochondriacs that have taken over all day-to-day aspects of ordinary existence. Right? My God, right? I could not have believed a few months earlier that such a thing is possible. Vasya is tested for a disease that afflicts 1% of the population. The test result is positive. Assuming this test is 95% reliable, what is the probability that Vasya has the illness? You understand what I mean by reliable? Reliable in this case, let's make it precise. Reliable means that 95% of the time, if you have the disease, the test will come positive. 95% of the time, if you don't have the disease, the test will come negative. You understand what I mean, guys? So it's a bit difficult of a question, but let's see what you think. Would you be worried if the test came positive and it were 95% reliable? Thank you, Naomi. Thank you, Abhishek. Thank you, Sophia. Right, guys, a little bit longer, and we will discuss this problem. Thank you, Erica. You're very good. I hope that means that you're actually solving it, right? You're not looking at my notes that are posted already a few days ago and you just know it. So if not, it's wonderful. I'm very proud of you, right? Even sad because when you know too much, then you're not surprised, right? I'm not entertaining you enough. All right, so yes, let's discuss this problem, or what? Or somebody is still working on it. Somebody still is trying to figure it out. Yes, thank you, Chabeli. All right, guys, let's do it. So this is how I thought of it. Okay, so first of all, let's D be the event that Vasya has the disease, and T is the event that the results come positive. By 95% reliability, I then mean that probability the test is positive given disease is 95%, and negative given no disease is also 95%. Yes? You understand? In the symbols, that means negative given no disease is 95%. And then what we wish to calculate is what's the probability that we have disease given that test is positive. So we can write it like this. We can say test is positive given disease. You see, I did it very fast. I skipped a step. You understand what the step is? I just write disease intersect test positive divided by probability test positive. And once I have the intersection in the numerator, I can decide that another thing is better to be first. So I'm saying test positive given disease, probability of disease, right? Because in the numerator I will have product of two events. So then I can decide which of those events I consider first and which I condition upon. So then we have this calculation. Good, guys? Probability the test is positive, it's positive if disease was about, or positive if disease was not present. Now we said that 1% of the population has the illness. That's important. So what do we have here? In the numerator, probability that he has disease before he got tested, it's about, it's 1%. That's the 1% here. And probability that if he has disease, the test will be positive is 0.95, 95%, yes? Same thing here on the denominator. And then what is this? Probability that test is positive given no disease. That must be, see, if no disease, then either test is positive or negative. It must be 5%. That's why it's 1 minus 0.95. Everybody says it. I think not everybody answered, so but many answered, I think. So you see this, guys? And then probability of no disease is 0.99%. And you see, what's the actual probability? 16%. The actual probability then is 16%. By the way, an interesting thing about it is that if you begin testing a population that has no disease and you test more and more and more, then you will say, my God, you know, disease is increasing exponentially. Of course, if you increase the tests exponentially, right? Good. So we have 16%. Now, why is the probability so low? Let's try to understand it a little bit better. Why is it so low? You think 95% reliability is pretty good. Most tests actually are probably much worse than 95% reliability. So I heard. I've never actually really, you know, I don't know how they work. But I heard that the reliability of 95% is extremely high. So let's see what happens here. So let's take a sample of 10,000 people. 10,000 people. Now, how many of them will be diseased? 1%, which is divide this by 100 and you get 1%, right? So it will be 100 people diseased. And the rest are healthy. No worries, guys. Good. So make sense, guys? So 100 people that are diseased and the others are healthy. And then of the diseased people, 95 will be correctly identified as positives and 5 will be incorrectly identified as healthy. So those are false negatives, right? You have true positives and this is a false negative, yes? Now, from the healthy population in this decision tree, we have that 495 will be identified as false positives because the test will identify incorrectly 5%. So if you take 5% of this number, you will get 495. Good. And the rest will be identified correctly as negative. So there are the true negatives. Now, what is my restricted sample space? My test came to be, if I'm one of this population, I either belong in this region or in that region because this is the test positive people. Do you agree? Test positive people, so I'm either among the 495 healthy or 95 unhealthy individuals. So then the probability is what? Look at it. The probability is if I selected randomly a person from this population, it's 95 plus 495, right? And out of them, I had to select randomly somebody that has the disease. So that would be 95 here, right? Which corresponds to the 16%. You understand? So they just in this population, there were quite a lot of positive tested people that are healthy. So the next question is, of course, if Vasya is tested again and the result is positive again, what is the probability that he is afflicted? Valeria says 15.2. Okay, thank you, Valeria. That's for the second time, you understand? So we're asking, you test twice, and twice the result is positive. Thank you, Sandy. Thank you. All right. Are you ready, guys? Let's look at the solution. So we can do it this way. We can continue the decision tree. So again, tested positive means that Vasya is either in this population or in this population. Now, if you make another test, then the likelihood that that the test will be negative is 0.95. And the likelihood it will be positive is 90.25, right? 95 of those people, 90.25 of them will test positive, right? So in other words, some person will have to cut into pieces. False positive, that would be test will be negative with likelihood 470. So out of those people, if we test them, 470.25 will test negative, and 24.75 will test positive. So the probability is 90.25 over 90.25 plus 24.75, which is about 78%. You understand how I did it? Again, because my sample space is now twice test came to be positive, so it's here. And to have the disease, you are one of those people, and not to have the disease, you're one of those people. So now it's 0.78. So having two positives make it very much more likely that the person has the illness. Here's another question of this form. You're saying I made some error. Well, you see, so let's see. So for test to be positive, what you do is you take from here, you take 90. You multiply this by 0.95. Yes, you multiply this by 0.95, and this you multiply by 0.05. Okay, and then if I made a mistake, sorry, right? So just you understand, basically obtain those sample spaces and correct for it. Have I made a mistake?
I think it's just that in the when you wrote tested negative, you put 0.95 instead of 95 times 0.05. So it should be, I think you were saying it should be 5.75.
Okay.
Or sorry, 4.75.
Yeah. So there is a 2 that's not supposed to be here. All right, but you get the point, right? So apologies for the error. Hard to avoid them. All right, so in an ongoing criminal investigation, the inspector is 60% certain that the suspect is guilty. New evidence shows that the perpetrator of the crime is left-handed. The suspect is left-handed. If 20% of the population are left-handed, how certain should the inspector be of the guilt of his suspect? Make sense, guys? So new evidence came, and we know definitely that the perpetrator of this crime, there was a single perpetrator, let's say, and that perpetrator was left-handed. And there is a one suspect, it's 60% likely that he was the criminal, and he is also left-handed. Thank you, Abhishek. Let's see what the others. I don't know. It looks to me like the problem is less difficult than the previous one. Maybe I'm wrong. Thank you, Naomi. All right, guys, still waiting for the rest of you. Thank you, Sandy. Thank you, interpret. Thank you, Melissa. Thank you, Stephen. Okay, just a few more. Wonderful, Syed. It seems that all of you are united so far. Makes me wonder, are you just seeing what the previous person wrote or looking into my solutions? I hope not. I hope you're just figuring it out. I'm very proud of that. Yeah. Let's go through it, guys. Yes. So you see enough of those and you then will know it's 0.6 divided by 0.6 on the denominator plus 0.2 times 0.4, right? And then, I mean, you just can simplify it. Okay, then now the reason is as follows. So let G be the event suspect is guilty and L event suspect is left-handed. Okay, And then we are assuming that probability of guilt is 0.6. That means that probability of innocence is 0.4. So that means that probability of guilt given left-handed is the same as probability of left-handed given guilt times probability of guilt, yes, divided by probability of left-handed, basically the same thing. And then we condition on not being guilty, right? So if the person is, we're assuming here that it's indisputable evidence that the criminal was left-handed. So if this guy is guilty, the probability he is left-handed is 1. You understand how this works? If he is guilty, the probability that he will be left-handed is 1. We recondition, we kind of ignore that we are or actually observe that he is left-handed. And then the probability that he is guilty is initially 0.6. Same thing on the denominator. Now, the probability he is left-handed given that he is not guilty is that I accidentally picked up somebody that is left-handed from the population. And that means it's 0.2. Yes? Times 0.4, which is the probability that he is not guilty. And that approximately is 88%. Okay? Now, here is generalization of Bayes' formula, right? So there is no reason to condition on only 2 outcomes, guilty or innocent. There is all this spectrum. In fact, you can condition into maybe infinitely many events. But here we just do finitely many. So suppose that F1 and Fn are mutually exclusive events and their union is the full sample space. In other words, if something happens, it happens in one of those outcomes and each of those outcomes is disjoint from any other outcome. You know, it makes sense, guys? So I just have maybe 3 possibilities, right? So for instance, you are either in my room or you are in room number 1, 2, 3, 4, or 5, let's say, right? So then there are 6 possibilities of where you are. And let's say that must be one of those rooms. So those are the events F1 through Fn, all the possibilities. So then the probability of E is the probability of E intersect F1 or E intersect F2 or E intersect Fn, all of them. Yes, because they are disjoint. You understand how I made it, right? It's just the intersection of E with S is then I can distribute E through the union, right? And then I take when the probability is additive. So I have this thing. And then I can condition, right? So I can condition what's the probability of E given F1, probability F1, plus what's the probability of E given F2, probability of F2, and onwards. And in simple form, it's written as the summation here. Okay. Here is hopefully simple enough. It's a bit abstract in symbols, but let me try to explain. So suppose that you know that a plane has crashed in one of 3 possible regions. Region 1, region 2, region 3, and you don't know which one, but it must be one of those 3. Now the probability of not finding the plane, if you look in region K, is 1 minus BK. This is actually not so easy to determine. I guess you hide the plane many times and you make the people search for it, right? And see how often do they find it, how many searches they find it. But somehow let's imagine that we have an estimate of this number. Right? So B sub K is the overlook probability. In other words, imagine that the plane is in region 1. B sub 1 is some sort of probability that I will not be able to find it. Maybe think of this as hiding a toy in your room, right? And then making your sister or brother search for that toy. Yes? And see how often will the sister or brother find where you hid it in that room. That's the idea, right? So you can kind of simulate this with hiding a toy in your room. So you have to have statistics for it, I presume, right? So so then the question is this: what is the probability that plane crashed in region K, where K is 1, 2, or 3, given that a search of region 1 was unsuccessful? You understand, guys, the question, right? So it's kind of there are symbols here, but really 3 regions. We searched region 1 and did not find it. Each region has an overlook probability. In other words, if the plane is there, you might not find it, even if you search. So you can only answer it symbolically of sorts. you may assume it's equally likely to be in any of the regions, right? It's equally likely to be in region 1, 2, or 3 before you search. All right, guys, I will reveal the answer as I have to hurry to finish the full lecture today. So this is how I'll label it. Rk is the event plane is in region K for K1, 2, 3. And F1 is event plane was not found in region 1. So what happens here is then I can begin solving what's the probability the plane actually is in region 1 given that it is not found in region 1. Yes? So that means what? That I mean, I do this conditioning thing. Do you get how it works on the denominator? It's basically the probability of F1 is F1 given R1, F1 given R2, F1 given R3. Good. Numerator is just F1 given R1, just the intersection, but I have it with R1. Good. You all understand, guys? This is the same formula. Very important. The generalized formula is very important. So I can cancel away probability R1, R2, R3 because they are the same. They are 1/3 each. I can cancel them out, and I have this is my fraction. You get it, guys? So the unrestricted probabilities we're assuming equal likelihood, so I can cancel them out. And here we go. So the probability that the plane is not found while being in region R1 is B1. In other words, it was overlooked. It was there, but search did not find it. And the denominator is B1 plus 2. Yes? Now, if you do the calculation for the remaining ones, now the probability it will not be found given Rk, similar formula, but given Rk where k is not 1, is naturally going to be 1. It will never be found if it's in a different region, right? It will not be found in 1 if it's in a different region. So this would be, numerator would be 1 and denominator is the same, as you should verify. And because the overlook probability is usually, well, it's not 0, right? It's not 0, so that means that that means that in general you're expecting the likelihood to increase, especially if the overlook probability is well, you see, basically the likelihood that it will be in a different region is going to be larger because this is 1 and this is less than 1 numerator. Good. So here is another problem, guys, of the same type. We have 3
Sorry, I have a
flashlights. Yes.
quick question about the one before.
Yes.
Why is the probability of P of F1 R2 and F1 R3 both 1?
Because that means what's the likelihood that it will not find? F1 is not find in region 1, right? If we're assuming the airplane is in 1 region, not in 1, right? So no matter how much I search region 1, I will not find the plane there. So that's why it's 1. Everybody understands, guys? So it's like a toy question because the difficulty in this question is really how do you determine the overlook probability? So here is another question. There are 3 types of flashlights in a bin. There is a flashlight of type 1, flashlight of type 2, and flashlight of type 3. And we are given what's the probability that each lasts more than 100 hours. If you have a flood or electricity is off, which one of them lasts, what's the likelihood each of them will last more than 100 hours? So the first flashlight, it's likely that it will survive for more than 100 hours. The battery is not going to be dead, is 0.7. For the type 2, it's 0.4. For type 3, 0.3. And then you have 20% of all the flashlights in the bin are of type 1, 30 of type 2, and 50 of type 3. And so problem A, what's the probability that a randomly chosen flashlight lasts over 100 hours? What's happening? I'm losing people. 17, 16. And I cannot even tell who am I losing. Thank you, Chabeli. Thank you, Erica. So let's solve this together, guys, right? You see, you can imagine it pretty fast. So we want the probability that it lasts for more than 100 hours, right? And that's very simply probability lasts more than 100 hours and flashlight type A, type B, or type C. Yes? So what's that probability? The probability is simply 0.7 times 0.2 plus 0.4 times 0.3 plus 0.3 times 0.5, right? You understand how you do it, right? It's if you think about it, you can actually do it even in your head, right? Good. Now then we have the second part of this question is asking, given that the flashlight lasted over 100 hours, what's the conditional probability it was of type J for J 1, 2, 3? So I let's not, because we're running out of time, I want to quickly just read it off, right? So probability it was type A, given it lasted more than 100 hours. Just, we already calculated the denominator. We know what it is, right? It was 0.41 for all of them. And that probability here is, you see, that probability is, of course, 0.7 times 0.2 is for the numerator. 0.4 times 0.3 is numerator here, and similarly for C. Makes sense, right? They are really identical problems with just different numbers. Good. Of course, the numerators must add up to 1, because whatever lasted more than 100 hours is supposedly one of the 3 flashlights. Good. The 41 is now, H is the sample space here, so to speak, right? Now, let's just make this question is slightly weird, guys, but I hope you understand what I'm getting at, right? Remember that I mentioned that in every question in probability, we are assuming far more than actually is given to us, right? So when you toss 2 pairs of dice, I imagine actually that I pretend that everything else except for the outcome on those 2 dice is known to me about the universe, right? Because the sample space is the possible universe that will come into existence once the dice are cast. So here is a simulation of why that's the case. So suppose that here is what's going to happen. We will pick 1 of 4 dice, and each of them is, 1 of them is blue, 2 is red, 3 is yellow, and 4 is white. And each of those dice is a fair die. You understand? Each of those dice is a fair die. Now the question is, given that sum on the dice is 7, what is the probability that the numbers 1 and 6 came up when I was tossing the die? You know, you understand? So one of those dice is picked and then tossed twice. But we don't know if there would be a preference to pick the blue die or the red die, or each of them is randomly picked. We know nothing about it, right? So the general sample space is what? Is the die that will be picked, and then what comes on the first roll, and then what comes on the second roll. But I'm going to say that I can assume that the die that's picked is die number 1. You understand? I can fill this with the number 1, and the probability that I will calculate will not be affected. The universe is certainly affected, right? But the probability isn't affected. Because so why is that the case? It's intuitively, I think you understand that that would be the case, because whenever you calculate this probability, you calculate it within the universe where either the first or second or third or fourth die is cast, right? So then we're assuming that one of those dice is going to be picked, in each of them with probability P1, P2, P3, P4, right? And the summation of those probabilities is 1. That gives us preferences, right? Maybe if I always decide to pick the red die, that means that red is 1 and everything else is 0. Good? So it gives me all possible preferences whenever I perform it. So then what's the situation? So I didn't use symbols, and that's actually somewhat a mistake. That's because I was rushing. So probability of 6 and 1, given that sum is 7, is probability 6, 1, sum is 7, divided by probability sum is 7. Okay, and then I can break the numerator into all this information, and it's die 1 plus all this information in die 2 plus all this information in die 3, and I do the same for numerator and denominator. You understand? Because I cannot tell how did sum 7 come about without knowing which particular die was tossed. Right? You understand? I need this information. I need to say that something happened there. And then I condition, look at it, you see? This is just conditional probability. And then I notice the following. So the probability that sum is 7 and 6 and 1 came about, given that die was die number k, is the same as if I assume that die number 1 came about, right? Because the sum of 7 given either die 1 or die 2 or die 3 is the same probability. So here is where I make the jump, you understand? Because they're the same probability. They're all fair dice. I can say this, right? I can assume that it's die 1 and then the probability that die k was picked. I switch this information to die 1 because this probability will be the same regardless of what actual die came around. That's by assumption here, right? And that allows me to factor out this term. Look at it. This term does not depend on k. So I can factor it out. Here you see, I factor it out in the numerator, and this is what ends up happening. I factor it out in the numerator, and I factor it out in the denominator, and I have this summation canceled out. You see, this sum is just 1 divided by 1. It's canceled out. And so what ends up happening is that I know now is that it's the same as the probability that 6 and 1 came about. Given that die 1 was tossed and sum came to be 7. And that probability is quickly 2 divided by 6, because it's either first toss is 1, second die is 6, or the other way around. So it's 2 over 6, which is 1/3. I hope you understand, guys, what I mean here. Right? So the entire argument, we can go over that again. I wrote it a little bit clumsily. The point is that I may assume more information. I don't delete this information. I just assume that I know it, let's say, to be die number 1. And I actually only have two parameters to consider, right? That's by generalized Bayes formula. I can see why that will be the case. So that information on which die was tossed in that sense does not matter. Not that it doesn't exist, but it's just that this information is filled in. All right, guys, so that is the end of today's lecture. If you want to stay for office hours or discuss some problems from the exam, please do so. And we can also discuss, I will write about it, but we can discuss how I want the submission to be done. Of course, I want it to be neat, precise, right, or organized, maybe on the written on the body of the exam, etc. So I'll stop the recording and we can go